Section 9-4, two dependent samples, or matched pairs. The idea behind here is to take a look at methods for hypothesis tests and confidence intervals where we look for the differences of values from two dependent populations. And the dependent populations are some sort of matched pairs. The hypothesis tests and confidence intervals that we're going to be using the same distribution and standard error. They're equivalent in the sense that they result in the same conclusions. And so because of this, we will be looking at the difference between them assumed to be 0. So we're going to be comparing things to 0. So there's no real fine procedure that we'll be using where it has a different value, but we're going to be using the difference in the means to be equal to 0. Here's an example. If we take a look at the matched pairs of U.S. presidents and the heights of their main opponents. It's been said that the taller person in the presidential race usually wins. I don't know if that's true, but this is one way to check. So there's 5 randomly selected presidents and their opponents, and then we have their heights here. So this is matched pairs. We have the president and the runner-up candidate who didn't win, and then we can match those heights as the paired data. So this is an example of a dependent set. Just a word on experimental design. When designing an experiment or planning an observational study, and we're using independent samples, we generally look at 2 independent samples. The advantage in using matched pairs is that we can reduce the extraneous variations that could occur if we were to look at them independently. Here's our notation. So we're going to use D instead of X. So D is the individual difference between the 2 values. So we're going to be looking at the population, the samples from one population minus the samples from another population, and then that set of data that we're going to collect there is going to be called D. Mu sub D is going to be the mean of the differences, and then for the population, that's the one we're going to be comparing. D bar is going to be the sample mean of those D values. S sub D is the sample standard deviation of those D values, and N will be the same, and that's going to be the number of paired data. The basic requirements, we want to assume that the sample data are dependent in the pairs that we're looking at. The samples are simple and random, and we want to either have a large enough sample, or we want to assume that it's coming from a normally distributed population. Here is our hypothesis test statistic, and if you look at it, it looks very familiar to our regular t-test, and that's because it really is. Imagine x bar minus mu divided by s over square root of n. That was our formula for our hypothesis, that's for our test statistic for the t-test. And here x bar just changed to d, mu sub d used to be mu, and s sub d used to be s. We'll use the same degrees of freedom of n minus 1. So we will be using, since it's a t-test statistic, we will be relying on table A3, or we will just be using our calculators to find our p-values or find our confidence intervals. Speaking of confidence intervals, this is our formula. Again, similar to x bar plus or minus e, where e is equal to the critical value, critical t-value, times s over square root of n. This time we're using the d's to take a look at our differences. So let's actually do the example. the example of the heights of those presidents and their main opponents. And so we have the first row being our first population, the presidents, our second row to be the runner-up populations of the sample from the population of runner-ups. And then now we introduce a third column, or in this case row, the difference D. So D would be the set of values 19, -12, 8, 0, and 1. Those are just the differences between the president and their main opponent. A quick check, we're going to assume that the samples are dependent because they're paired. We got the president and runner-up pair. The pairs are randomly selected. They're simple and random. And then the 5 data points is a really small set of points, but we'll just assume that they're normal. And here's the normality check that they have. So our claim is that the difference is going to be greater than 0. So remember that the presidents was the first value, and then the runner-ups were the second value, and we subtracted them. So if the presidents were assumed to be taller, or we're checking to the claim that the presidents were taller than the runner-up, the winners were taller than the runner-ups, then the first value would be larger than the second value, which is to say that the differences would be positive. And so that's what the original claim turns out to be. Now, the original claim is not true, then mu is less than or equal to 0, and this is where we get our condition of equality. And so the condition of equality becomes an equal sign for the null hypothesis, which means our claim is the alternative hypothesis. And this looks like it might be a typo. This should be possibly a 0 or a 1 or an A. So let's fix that real quick. And here is our set of hypotheses, the null and alternative. We'll use a 0.05 significance level, and we're going to use a t-distribution using the t-test. And our statistics are x bar, or d bar in this case, is 2.3. S, the standard deviation for the sample, is 11.4. And our n is really small. N is equal to 5. So we'll punch that into our formula, and we're going to get a test statistic of 0.628. And we're going to look at our table A3 with the degrees of freedom equal to 4 and an alpha significance level of 0.05, and we get a critical value of 2.132. Now our test statistic is 0.6, so that is not in the critical region. So our conclusion will be to fail to reject the null hypothesis. So this is if we were using the critical region method, critical values. So let's use our calculator to find the p-value. Using the p-value method, we take our calculators. Now to get ourselves ready, we will take a look at the first population and the second population, and we'll put that into L1 and L2. Now the differences we can get by subtracting L1 minus L2 and then putting that list in L3. So now the numbers that we saw before, 19, -12, 8, 0, and 1, are done by my calculator here by doing this L2 minus L3. So if you type in your L1 list and L2 list, and then you move your cursor up to L3 and then type L2 minus L1 and press enter, you're going to get these values. Once you have the values for L3, you're going to go into the t-test, and then you will use data, because you have your data stored in your calculator. You will put 0 for your mu sub 0, because remember the difference that we're looking at between the two populations is 0. That's our null hypothesis. we're going to access our list 3. Frequency is going to be equal to 1. And in this particular problem, we were looking at a right tail test. And so we ask it to calculate, and then we will get our test statistic to be 0.628 or 0.628 that we saw earlier. And then now, more importantly, we get our p-value. So our p-value is 0.282. So 0.282 is larger than our significance level alpha. So because the p-value is larger than 0.05, we will fail to reject the null hypothesis. And so we come to our conclusion: there is not sufficient evidence to support the claim that the population of heights of presidents and their main opponents, the difference have a mean that's greater than 0. So that's also to say that the presidents don't appear to be that much taller than their opponents. Not statistically, at least. Not statistically significant. Let's shift over to the confidence interval. Let's find a 90% confidence interval to estimate mu sub d. And so after we find our margin of error, we can plug that into the formula, and we get mu sub d is to be estimated to be between negative 7.7 and positive 14.1. So this is now a case where we go from a negative number to a positive number, so it looks like 0 is going to be involved. And whenever 0 is involved, we can say that the two samples or the two populations don't seem to be significantly different. Let's take a look at the calculator method of finding the confidence interval. Again, we'll start off by putting our values into L1 and L2 and doing the subtraction and storing that into L3. And then we're going to do a t interval on L3 using the data option in your t interval. And then you're going to get the same results. We get negative 7.7 and positive 14.1. And so with the 95% confidence, the limit of negative 7.7 and positive 14.1 contain the true value of the difference in heights. The heights of the presidents minus the heights of their runner-up opponents. So we see that the interval does contain 0, so it's possible that the mean difference is equal to 0, which is to say there is no significant difference between the two. Okay? Alright, that is the end of 7-4, or I'm sorry, that is the end of 9-4, and that is the end of Chapter 9. So all this stuff is a continuation from Chapter 8, where we've established the hypothesis testing, and also from Chapter 7, where we built up our confidence intervals. So we're doing hypothesis testing and confidence intervals for 2 samples or 2 populations. All right, good luck.